Hi, Washington Liberty Chemistry students. This is your Unit 3 lesson on atomic mass. And as many of you probably know, atomic mass is one of the important pieces of information found on the periodic table with each chemical symbol. But what is it? So we're going to start out by going back to something that you're very familiar with. And this will lead us to what the atomic mass is. So just go with this for a minute. Now suppose you needed to determine your test average in a class and you had taken 5 tests and you can see these are your scores. You got 100 4 times but you had a bad day and got a 50. Now what would your average be? Now many of you might be able to do this in your head, but go ahead and calculate what your average in the average test average would be, the average score. What did you get? Well, you would have gotten your average is 90. Wow, you still have the A. But you might notice that not a single one of these scores is actually 90, right? And again, why is it 90? You've got 4 100s. Why is it 100? Why isn't it 50? That's your lowest score. Or why isn't it 75? And the answer to that is you have more 100s than you do the 50. This is what's called a weighted average. Your average is 90. Now you'll notice the average does not match any of the actual scores though. So there are a couple of different ways to do this, to find an average. You probably used method 1. And go ahead and use method 1 to calculate what the average would be. Again, you probably just add it. You may have done this in your calculator, may have done this in your head, added together, divided by 5 to get your answer. But I want you to see that all 3 of these methods would gain you the same answer. So in your calculator, you may want to pause the video and just try it. So you see we've got 4 100s. So instead of going 100 plus 100 plus 100 plus 100 in your calculator, you might have just done 4 times 100, or you might have done that in your head and said that was 400, added to 50, divided by 5. An equivalent method would also be you've got 5 scores, 4 of them, or 4/5 of them are 100. That's 80% of your scores. So 80% of your scores are 100, 20%, 1 out of 5 was 50. So if you do 80 times 100 plus 20 times 50 divided by 100, you're going to get the same answer. And again, 80 over 100 is the same thing as 0.8. So 0.8 times 100 plus 0.2 times 100 gives you 50. You'll see if you do all 4 of those methods, they are valid ways of using that same data, 4 100s and a 50, to calculate your average. Okay? Now, I want you to try this problem. This time you can't see the individual scores, but you have been given the percentage of your grade and your average for that particular category. So you might be in a class where 40% of your grade is based on assignments, maybe homeworks, various other things, and 60% is based on your test grades. And on your assignment average, you have an average of 85, and your test average is 95. So what would your grade in that class be? Would it be a 90? Can you figure out how to do a weighted average like we did in the methods before? So if you used one of the methods before, you would actually find that your grade in the class is a 91. It's not a 90. Now, why is it closer to 95? Why isn't it 90? Well, more of your overall average is based on tests. And so it would make sense that the average of the grade in the class, since 60% of your grade is determined by test grades, would be closer to the 95. So you could have used method 3 or perhaps even method 4 to have done these weighted averages. So 40% of your score was an 85 and 60% of your grade was a 95. And so if you want to do a weighted average, it would just be 40 times 85 plus 60 times 95 divided by 100. In other words, you can kind of think of it as like if I had 100 assignments, 40 of them would be 85% and 60 of them would be 95%. So by doing this, you're basically adding up 100 scores and dividing by 100, and you get 91%. Now remember, you can always express the percentage weight as a decimal directly. So 40 over 100 is 0.4, 60 over 100 is 0.6. Notice there's then no division here because we've already done the division in the decimal. So if you put 0.40 times 85 plus 0.60 times 95, you'll get 91, which was your average. Okay, so now what does this have to do with atomic mass? Well, I want you to recall the definition of isotopes. Remember, isotopes are elements that have the same number of protons and therefore are the same element, but have different weights, different masses, because they have different numbers of neutrons. So for example, if we have carbon 12, carbon 13, and carbon 14, what does that mean? Well, it means that carbon 12 has 6 protons and 6 neutrons. 6 and 6 gives you 12. This is the mass number of this particular element, which is just the protons and the neutrons. Remember, for the mass number, electrons are so insignificant that we don't count them. Now, carbon 13 just has 1 extra neutron. Notice all isotopes have the same number of protons. That's what makes them carbon. So 6 plus 7 gives us 13 as the mass number, and 6 plus 8 gives us carbon 14. Okay, again, what does this have to do with the atomic mass? Well, okay, so we've got these 3 different existing isotopes of carbon, and this one is pretty much close to 12, 13, and 14. But when you go and look on the periodic table at the atomic mass, what it says on the periodic table is 12.01. It doesn't say 12, it doesn't say 13, it doesn't say 14. Now, why does it say 12? And in fact, if you get one that's a little longer, it says 12.011 atomic mass units. Why? Well, you got to think about what the difference is between these terms: atomic number, mass number, and atomic mass. Now, remember from the last lesson, atomic number is the number of protons. It is the ID number of the element. It tells you the symbol. They always correspond. Like carbon always has 6 protons, and that's carbon. If it has 7 protons, it's nitrogen, and you find that on your periodic table. Now, the mass number is a way of telling us the differences in the mass of the various isotopes. And again, this is for an individual atom. So the mass of the protons plus the neutron in a single isotope in atomic mass units is the mass number. So you're literally just like with the carbon, 6 protons, 6 neutrons, the mass number was 12. Or 6 protons, 7 neutrons, the mass number was 13. Now note the difference here in atomic mass, the thing that actually appears on the periodic table. The atomic mass is the weighted average of all the isotope masses. In other words, it's the average mass. Now on the periodic table, we'll learn about this later, but it is also the mass in grams of 1 mole, or this huge number of atoms, 6.02 times 10 to the 23rd atoms of the substance. So it's an average weight of the isotope, okay? And it's a weighted average, kind of like your score for your grades were weighted. And where do we get the weights? Well, we look at something called isotopic abundance, but let's look at an example. So let's look at lithium, okay? Just a little background about lithium. Lithium is often mixed with aluminum and magnesium to make very lightweight alloys, mixtures of metals to be used in an aircraft. Lithium is really the lightest metal on the periodic table. So lithium, why is lithium's atomic mass 6.941? If you look on the periodic table under lithium, where the atomic mass is, it's got an atomic number of 3, has 3 protons, but its atomic mass is 6.94. It's not exactly 6, it's not exactly 7. Why is it listed as 6.94? Okay. Well, let's look at this data. Lithium has 2 isotopes that must be averaged, and they are not equally abundant. There's not an equal percentage of each. In other words, it's not 50% lithium-6 and 50% lithium-7. Lithium-6, which has 3 protons and 3 neutrons, and has an exact mass of 6.015 in AMUs, is only about 8% of all the lithium you're going to find out there in the universe. So if you had 100 lithium atoms in front of you, and you started plucking them out, around 7 or 8 of them out of those 100 would be lithium-6. You'd pull it out, you'd look at the nucleus, you'd see it had 3 protons and 3 neutrons. About 7 out of 100, 8 out of 100 would be that way. Most of the lithium, 93% of it, would be lithium-7, the isotope that has 3 protons and 4 neutrons. So you can see there's a lot more lithium-7. So again, just like if this were your test bucket and it counts more, then in the weighted average, which is what the atomic mass is, you would have to weight the weight of lithium-7 to be more important. So we're going to use essentially method 3 to figure out the atomic mass. It's a weighted average. So it's always the percent times the mass over 100, or you can do the decimal equivalent. I always get mixed up with decimals sometimes. So I like to just do the percent times the mass plus the percent times the mass and just divide everything by 100, and then I know I've done the average right. So it was 7.49% lithium-6, which had an exact mass of 6.015, and it was 92.51% lithium-7, which had an exact mass of 7.016. So we just multiply, divide by 100, and we get 6.94 AMU, which is what we see on the periodic table. And you can see the average is closer to 7 because the isotope that is lithium-7 is more abundant. Just like your average on those for your grade was closer to your test grade average because it's counted more, it's weighted more than the other averages. So you can always tell sort of which isotope might be more abundant based on what you're closer to. So now I want you to think about this for a second in terms of averages. If I had a whole bunch of lithium atoms and I reached in and I started weighing them and I'm looking at the nucleus, is there any atom of lithium that's going to have a mass of 6.94 AMU? And the answer to that is no. It's an average mass, okay? So we always work with more than one. We know the mass of each individual atom, but if we always work with more than one. So it's an average, just like your average in the grade was 91%, or your test average was a 90% in that first example, but not one of your scores was a 90%. It was an average. So 6.94 is an average. If you have a bunch of lithium around, then it's going to average out to 6.94. Okay, now you might be asking yourself, and just for funsies, how do you find the mass of an atom anyway? Well, you use something called a mass spectrometer, and it uses a magnetic field to deflect. You basically get a sample of whatever you want. You heat it up really high, you vaporize it. So it has to be really hot, and it is also ionized. In other words, it has a charge attached to it when you do this. And then you use a magnetic field. You run it through a mass spectrometer, which uses a magnetic field to deflect the particles. And the lighter isotopes will be deflected more. And there's a little amplifier and detector and chart recorder that allows you to see the percent abundance of each of the isotopes. So let me just show you an example. This is an output for an element called molybdenum, and it has 7 different isotopes. And someday when you take IB or AP physics, AP chemistry, you're going to use this to figure out the percent abundance. But you can see that molybdenum has a lot of different isotopes. It has one that's molybdenum 92, 94, 5, 6, and again, the height of these lines tell you the relative percentage. So what you would do in an IB class or an AP class is you would measure all the lines, add up the total length of all these lines, and then measure a single line and figure out what percent of the overall is that particular isotope. Okay, now so molybdenum has a lot of different isotopes. Okay, so last question to see if you get this. So got a lot of different elements on here, but let's focus here on chlorine-35 and chlorine-37. You can see their natural abundances are 75.77 and 24.23. And take a look at their periodic table, and you can see what their atomic masses are. Chlorine-35 actually weighs or has a mass of 34.9688, so forth, and chlorine-37 is 36.965, and it's 24%. So are you going to find the atomic mass to be either 34.96 or 36.96 on the periodic table? No, you're not. Why not? Because the atomic mass on the periodic table is an average of all the isotopes. On the periodic table, you'll find the atomic mass is 35.45 for chlorine. Now, that doesn't match either one of those, but it is closer to the atomic mass for chlorine-35, which makes sense because chlorine-35 is more abundant. And that is your lesson on atomic mass.